ethyl alcohol reacts with ethyl chloride in presence of pyridine. What is the product here? Okay, so let's see this reaction. Ethyl alcohol, that is CH3 CH2OH, when it reacts with the thionyl chloride SOCl2 in presence of the pyridine, right, in presence of the pyridine. So basically here in this reaction the hydroxide group is being replaced by the chlorine, so this is actually an acid reaction, a nucleophilic substitution reaction. So from the ethanol, the hydroxide group is being replaced by one of the chlorine atoms here, and then what do you get? You can get the product CH3 CH2Cl. Okay, so one of the products is this one. And what are the other products? See, the thionyl chloride here, basically in the SOCl2, if you have a molecule like this, SOCl2, one of the hydroxide group is being replaced, that is being replaced here by the chlorine, and that OH group then, initially in the mechanism you see that this hydroxide group actually is attached with this one, and then this hydrogen and the chlorine is lost from the molecule, and what you get? You get the other product will be the hydrochloric acid, and you get the sulfur dioxide. Okay, so you get the sulfur dioxide also. So the other products are HCl and the sulfur dioxide, both are the gaseous components here in this reaction. And this method of preparing the alkyl halide from the alcohols is treated as the best method from the industrial point of view, because here you get a pure product. You get the ethyl chloride, and the other components here are gases. HCl and the sulfur dioxide, they move in atmosphere. Okay, so they evaporate and you get the pure ethyl alcohol. So the option B here. Another reaction here is alcohols react with the halogen acids, and again the halogen that replaces the hydroxide. So again this is an acid reaction, a nucleophilic substitution reactions here. And the reactivity of different alcohols with a particular halogen is different, and similarly the reactivity of the different halogen acids with the alcohol is again different. Okay, it's not the same. So basically the order will be this one: HO, HBr, HCl and HF. It's because that the nucleophilicity of the different halide ions decreases in this order. I negative is a very strong nucleophile, then a Br negative, then Cl, then the F negative. That's why the reactivity of the different halogen acids towards the one alcohol is like this. Similarly, we can say that the reactivity of the different alcohols with a particular acid, right, halogen acid, will be different. And normally the tertiary alcohol, the 3-degree alcohol, that is more reactive than the secondary one, which is more reactive than the primary alcohol. Okay, towards the one halogen acid. It's because that in these reactions, in this reaction basically it is the carbocation that you get as an intermediate. Okay, you have a alcohol, and if you have a alcohol, a tertiary alcohol, and you react with the halogen acid here, so what happens in this, in the acidic medium when you use a particular halogen acid? So basically first there is a protonation, it attacks on it, and then you get an intermediate there. Okay, you have an oxygen now attached with the 2 hydrogen atoms. Okay, and now this oxygen has a lone pair electron, a positive charge, because it forms a coordinate bond with one of the hydrogen atoms over here. And then after that, water is lost here, and you get an intermediate carbocation. All right, you get a carbocation as an intermediate, and then it's a nucleophile, in the next step that attacks on the carbocation. So I negative will attack on it, and what you get? You get the you get the halogen, you get alkyl halide. Okay, and the different the stability order for the different types of carbocations is the tertiary is more reactive, more stable than secondary, than the primary one. Okay, so the stability of the carbocations decreases in this order. That's why the tertiary alcohol is more reactive. Tertiary carbocation is more stable than secondary than primary. That's why from the alcohols, if it's a tertiary alcohol, it will form a more stable carbocation. That means the alcohol will be more actual. In the reaction of C3-dimethyl 2-butanol with the hydrochloric acid, you get two products, A and the B. We have to find the two products. So again, this is a nucleophilic substitution reaction. Let's write down the structure first. It is the 3,3-dimethyl 2-butanol, means you got like this, CH3C, and it also has the 3 methyl groups attached to it, CHOH, and this is the CH3. Now if you react with the halogen acid with the hydrochloric acid, this hydroxide group will be replaced there. Alright, it will be replaced there and the chlorine will be there. So this is an SN reaction. You get alkyl halide. But what are the products that you get? We have just discussed that in the acidic medium, first what happens? This hydroxide group is lost due to the protonation on it, and you get a carbocation. Right? It forms a coordinate bond. OH forms a coordinate bond with it, and then the water comes off. So once water comes off, you get a carbocation over here. Alright, so you have a carbocation like this. See, you have a secondary carbocation. You get a secondary carbocation. And now, if the nucleophile in the next step attacks on it, what do you get? You get a substitution product, right? So you expect like this: Cl, H, CH3, 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 and the CH3 over here. So the only change is, rather than OH, you have a chlorine here now. This is one of the products that you expect. But we know that the carbocations can undergo rearrangement, and the rearrangement is only possible if you get a more stable carbocation. We know that the stability of the carbocations is in the order of tertiary, more stable than secondary than primary. Okay, so here in this carbocation, which is a secondary carbocation, you can rearrange to the tertiary one by the methyl shift here. This CH3 group, along with the electron pair, it shifts completely to the carbocation. Then what do you get? You will get the carbon over here, the positive charge here, methyl group is here, CH3, CH3, and H is here. Now see, this particular carbocation is a tertiary carbocation. This is a 3-degree carbocation, so this is more stable here, right? So this is more stable here. So secondary carbocation shifts to the tertiary carbocation due to the methyl shift. Okay, we can say this is the methyl shift here. So due to the methyl shift, you get a tertiary carbocation. And now when the nucleophile Cl negative attacks on it, you get another product, CH3, CH3, Cl here, CH3 here, H is here, and the CH3 is here. So in the reaction mixture, basically you have both the carbocation. Initially you get a secondary carbocation, but the secondary carbocation can rearrange to the tertiary carbocation, and that's why you find the two products. Since tertiary is more stable, that's why this will be the major product here, and this is a less stable secondary one, so this will be the minor product. So now we can easily find the major and the minor. So A here is the major, so this is the A product here. The minor is B, so that is this one. Hope you got it. Thanks for watching the video. Bye for now.